Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
This episode was generated using artificial intelligence. Please verify facts.
Hey, Herman and Corn. I'd like to chat today about an important topic in computing for environments where downtime is not an option. And I want to use again my little home server V1 breakdown as an example, because it's an application that was essential, but it's not something that I'm going to actually set this up for, because it just wouldn't be. I don't think it would be worth doing for almost anything you're hosting at home. But it does provide a fairly simple example for how this works. So let's say that I wanted to set up the environment to account for things like exactly what happened to my home assistant, or the computer it was running on, which is that the motherboard failed. So you have motherboard failure, or the PSU or the GPU or the CPU or whatever, some part in the computer fails, and that service is now offline. It's unavailable. The hardware has broken. So in this context, you move towards recovery if you can preserve that data. You might need to get the new part. But while that's going on, in a more professional setup, you have this concept of high availability and redundancy. So you might have two computers, or this is how I've always heard it explained. You have two computers, and when you're updating server one, the production server, let's say, you have copy on write, so that server 2 is always kept in sync, so that when you fail over to the failover server, and you have a load balancer in front of these two servers with uptime detection. So if server 1 production server is available, that's where traffic gets routed, and then there's this update process on server 2. Now, in the event that server 1 fails and you have to route to failover server, you're going to be updating that. And in an ideal recovery situation, ideal meaning it's so good that the end users have no idea that a computer just broke down in the process. Let's say server 2 is being updated, so now it's ahead of server 1. We're trying to get server 1 back online, and when it does happen, we need to sync those changes from server 2 back to server 1 before routing traffic back to it, because it's now ahead of server 2. So Herman and Corn, that's the kind of mental layout I have for a high availability situation. Let's talk about how that works in practice with enterprise grade tech, where we do have those, or even in cloud computing environments for that matter, where we do have entire servers whose purpose is just to be on standby in case hardware failure occurs on server 1. Let's talk through that whole cascade, failing over to the redundant server, failing back when the primary is brought back online. And let's talk about how that actually works in practice. Over to you two.
Hey everyone, welcome back to My Weird Prompts. It is February 14th, 2026, and while some people are out for Valentine's Day dinners, we are here in the glow of our monitors. I am Corn, and I am joined as always by my brother, the man who once tried to cluster two calculators just to see if they would share the load, Herman Poppleberry.
Hello. It is great to be back in the studio, which, for our new listeners, is actually just our living room here in Jerusalem. The hum of the servers in the corner provides the perfect ambient soundtrack for today's discussion. We have a really grounded yet technically deep prompt today from our housemate Daniel. He has been having some major trouble with his home server lately. Apparently, his motherboard gave up the ghost, and it took his entire Home Assistant setup offline. No smart lights, no automated coffee, no security dashboard, just a cold, dark house.
Yeah, Daniel was telling me about that this morning. It is that classic sinking moment where you realize how much you rely on a single piece of silicon until it stops working. It is the digital equivalent of your car breaking down on a highway, but it sparked a great question from him. He wants to know how this works at scale. In professional enterprise or cloud environments, where downtime is not just an annoyance but a massive financial or operational risk, how do they handle these kinds of failures? If a bank's motherboard dies, the world does not stop. How?
That is a brilliant rabbit hole to go down, Corn. High availability and redundancy are the invisible pillars of the modern internet. When you think about services like your bank, or a major streaming platform, or even the power grid, they cannot just go dark because a single component in a data center failed. They use a whole architecture designed to expect failure rather than avoid it. In the industry, we often talk about the 5 nines, or 99.999% uptime. That only allows for about 5 minutes of downtime per year. You cannot achieve that by just buying expensive motherboards.
I love that framing. Designing for failure. It sounds almost pessimistic, but it is actually the ultimate form of preparation. So, Daniel mentioned this concept of failing over to a redundant server and then failing back. Let us start with the basics of that redundancy. In a professional setup, you are not just hoping your hardware stays healthy, right?
That is the key thing. The first rule of high availability is that there is no such thing as a single point of failure. If you have one server, you have 0 servers when it breaks, so you start with at least 2. Now, there are a few ways to set this up. The most common one Daniel touched on is what we call an active-passive configuration. You have one primary server doing all the work, and a secondary server sitting there, essentially idling, but ready to take over at a moment's notice.
But is not that a bit wasteful? Having an entire server just sitting there doing nothing while you pay for the electricity and the hardware?
It can be. That is why many modern enterprises move toward an active-active configuration. In that setup, both servers are working at the same time, sharing the load. If one dies, the other just picks up the remaining slack. It is more efficient, but it is also much harder to manage because you have to ensure that both servers are perfectly in sync at every microsecond. Whether it is active-passive or active-active, the goal is the same seamless transition.
But how does the secondary server know when it is time to step up? If the primary server has a catastrophic motherboard failure like Daniel's did, it cannot exactly send a polite email saying, "Hey, I am dying, please take over now."
That is where the magic of heartbeats and health checks comes in. In a high availability cluster, these servers are constantly talking to each other. They send small packets of data, often called heartbeats, over a dedicated network link. It is like they are constantly saying, "I am here, I am here, I am here." If the secondary server stops hearing those heartbeats for a predetermined amount of time, say 3 seconds or even less, it assumes the primary has failed.
But what if the primary server is not actually dead? What if it is just really slow, or the network link between the two servers is broken? Could you end up with both of them trying to be the leader at the same time?
Oh, you have just hit on the most terrifying scenario in distributed systems. We call that split brain. Imagine if both servers think they are the primary. They both start writing to the database, they both try to process transactions, and suddenly your data is a complete mess. It is like 2 people trying to write on the same piece of paper at the same time. To prevent this, professional setups use something called a quorum or a witness.
A witness? That sounds very legalistic, like they need a notary to sign off on the failure.
It kind of is. Usually, you will have a third, very small entity, maybe just a simple script or a third, low-power server that acts as a tiebreaker. If the 2 main servers lose contact with each other, they both check in with the witness. Only the one that can talk to the witness is allowed to stay active. The other one has to shut itself down or stay in a passive state. It is a way of ensuring there is always a single source of truth. We use consensus algorithms for this, like Raft or Paxos. These are mathematical ways to ensure that a group of computers can agree on a single state, even if some of them are failing.
That makes sense. So let us say the heartbeat fails, the witness confirms it, and the secondary server decides to take over. How does the rest of the world know to start talking to the new server? If I am a user trying to access a website, my browser is still trying to talk to the original IP address of the primary server.
This is where the load balancer or a virtual IP address comes into play. In a professional environment, users do not usually talk directly to the server. They talk to a load balancer that sits in front of the servers. Companies like F5 or software like Nginx handle this. The load balancer is the one doing the health checks. When it sees that server A is down, it simply stops sending traffic there and starts routing everything to server B. To the user, it looks like a tiny flicker in latency, or maybe they just have to hit refresh once. In very high-end setups, they use something called Anycast, where multiple servers across the globe actually share the exact same IP address, and the internet's routing system just sends you to the closest one that is currently responding.
So the load balancer is like the traffic cop. But what about the data? Daniel mentioned copy on write and keeping things in sync. If the primary server was processing a bunch of data and then died, how does the secondary server know where it left off?
That is the hardest part of the whole cascade, corn. Keeping state consistent. If you are just serving a static website, it is easy. Both servers have the same files. But if you are talking about a database or an application where users are constantly changing things, you need real-time replication. There are two main ways to do this, synchronous and asynchronous.
I am guessing synchronous is more reliable but slower?
Precisely. In synchronous replication, when a piece of data is written to the primary server, it is not considered finished until it has also been written to the secondary server. This ensures they are always identical, but it adds latency because you have to wait for that network round trip. Asynchronous replication is faster because the primary writes the data and then tells the secondary about it a few milliseconds later. The risk there is that if the primary fails in those few milliseconds, you might lose a tiny bit of data. This brings us to two very important acronyms in the industry, RPO and RTO.
More acronyms. Lay them on me.
RPO stands for Recovery Point Objective. It is basically asking, how much data can we afford to lose? Is it 0 seconds of data, or is 10 minutes okay? RTO stands for Recovery Time Objective. That is asking, how long can the system be down before it is back up? For a bank, the RPO must be 0. They cannot lose a single cent. For a video streaming site, an RPO of a few seconds might be fine.
This is where businesses have to make those tough calls. How much data loss is acceptable versus how much performance are we willing to sacrifice?
You are right. And it is not just about the speed of the network. It is about the integrity of the write-ahead logs and the database engine itself. If you're using something like Microsoft SQL Server or PostgreSQL, they have specific modes for high availability that manage this replication automatically.
Okay, so we have failed over. The traffic cop load balancer has moved the traffic, the secondary server is up and running with the replicated data, and the users are happy. Now, back at the ranch, the IT team has replaced the motherboard on the primary server. It is back online. This is the failback process Daniel was curious about. Why not just flip the switch back immediately?
Because that is where you can actually cause a second outage if you are not careful. When the original primary server comes back online, it is now out of sync. While it was being repaired, the secondary server has been taking new data, new orders, and new updates. The primary is now a time capsule of how things looked when it died.
Right. So if you just point the traffic back to it, you are effectively traveling back in time and losing all the work done while it was down.
That is it. We call this the resilvering or resynchronization phase. The failback process has to be a very deliberate sequence. First, you have to resynchronize the data in reverse. The secondary server, which is currently the active one, has to push all the new data back to the original primary. Once they are perfectly in sync again, you can start the process of moving the traffic back.
Is that usually done all at once, or do they do it gradually?
Usually, it is a controlled move. You might move 10% of the traffic back to the primary, see if it holds up, check the error rates, and then slowly ramp it up to 100%. In some very advanced setups, they might not even bother failing back right away. If the secondary is doing a great job, they might just let it stay the primary and let the old primary become the new passive backup. We call that a floating role. It reduces the number of transitions, and every transition is a moment of risk.
That seems more efficient. Why fix what is not broken? But let us zoom out a bit. We have been talking about 2 servers in a room, but Daniel also asked about cloud computing environments. How does this scale when you are talking about thousands of servers across the globe?
The cloud takes these concepts and adds layers of abstraction that are honestly mind-boggling. Instead of just thinking about servers, we think about availability zones and regions. An availability zone, or AZ, is essentially one or more discrete data centers with redundant power, networking, and connectivity. When you set up a high availability service in the cloud, you do not just put two servers in the same building. You put them in different availability zones.
So if a backhoe cuts a fiber optic cable to one data center, or there is a major power outage in one part of a city, your service stays up because the other availability zone is miles away on a different power grid.
Precisely. And you can take it even further with multi-region redundancy. You could have your primary setup in Northern Virginia and your backup in Ireland. If an entire coast of the United States has a massive internet backbone failure, your traffic can be rerouted across the Atlantic. Of course, the latency there becomes a huge factor, and the cost of keeping all that data in sync across an ocean is significant. In 2026, we are seeing more AI-driven orchestration that predicts these failures before they happen by analyzing patterns in hardware heat or network jitter.
It sounds like a constant balancing act between cost, complexity, and the level of risk you are willing to tolerate. I mean, for Daniel's home server, he probably does not need to pay for a second server in Ireland just to keep his smart lights working.
Probably not. But for a global enterprise, the cost of an hour of downtime can be millions of dollars. When you look at it that way, paying for redundant infrastructure across multiple regions is actually the cheaper option. It is like an insurance policy that also happens to make your website faster for users in different parts of the world.
You know, what strikes me about this whole discussion is that it is not just about the hardware. It is about the software that manages the hardware. You mentioned the load balancers and the heartbeat scripts. In the modern cloud world, is most of this automated, or is there still some poor engineer getting a page at 3 a.m. to flip the switch?
Ideally, it is 100% automated. We talk about self-healing infrastructure. The goal is that the system detects the failure, initiates the failover, and alerts the engineers only to tell them that it has already handled the problem and they just need to replace the faulty hardware whenever they get a chance. But, as anyone who has worked in tech knows, automation can fail too. Sometimes the failover mechanism itself is what causes the outage. We have seen cases where a false positive health check caused a massive cascade of servers shutting themselves down in a panic.
That is the ultimate irony. The thing meant to prevent downtime is what causes it.
It happens more than you would think. There is a famous concept called the observability gap. If your monitoring system is not seeing the failure correctly, it might try to fail over when it should not, or fail to a server that is not actually ready. That is why testing these failovers is so critical. There is a practice called chaos engineering, which was popularized by Netflix. They actually have a tool called Chaos Monkey that randomly shuts down production servers during the day.
Wait, they intentionally break their own stuff in the middle of the day? That sounds like a heart attack for any IT manager.
It sounds crazy, but the philosophy is that if you know your system can handle random failures at 2 in the afternoon when everyone is in the office and can fix it, then you do not have to worry about it failing at 2 in the morning on a Sunday. It forces the developers to build highly resilient code from day one. You cannot rely on a single server if you know the Chaos Monkey might kill it at any moment. Today, companies use entire simian armies with tools like Chaos Kong that can simulate the failure of an entire data center region.
That is a fascinating mindset. It turns reliability from a defensive task into a proactive design choice. I wonder if Daniel should set up a little Chaos Monkey for his home server. Maybe it would have forced him to have a backup motherboard ready.
Well, maybe not a backup motherboard, but it definitely highlights the importance of backups in general. This is a hill I will die on, Corn. Redundancy is not a backup.
That is a really important distinction. Can you elaborate on that? I think people often confuse the two.
It is a vital point. Redundancy is about uptime. It is about keeping the service running right now. If a server dies, you have another one. But if a piece of malware encrypts your database, or a developer accidentally runs a command that deletes all your user records, that change will be replicated to your redundant server instantly. Redundancy will faithfully and efficiently replicate your mistakes or your disasters.
Oh wow! So your high availability system will actually help the malware destroy both of your servers at the exact same time. It is like a high-speed conveyor belt for errors.
That is right. Redundancy keeps the lights on, but backups are what let you rebuild the house after a fire. You need both. In a professional setup, you have your high availability cluster for the immediate failover, but you also have point-in-time snapshots and off-site backups so you can roll back to how things looked an hour ago or a day ago if something goes fundamentally wrong with the data itself.
It is like having a spare tire in your car, which is redundancy, versus having insurance that will buy you a new car if you crash it, which is the backup.
That is a perfect analogy. And just like a spare tire, you have to make sure it actually has air in it before you need it. A lot of companies realize their failover process does not work only when the primary server actually fails. They have the spare tire, but it has been flat for 3 years.
Which brings us back to the failback. I imagine that is the part that gets tested the least. Everyone is so relieved that the failover worked and the site is back up that they might be hesitant to touch it again to move things back to the original server.
Definitely. Failback is often the scariest part because it is a manual or semi-manual choice. You are intentionally introducing a change into a system that is currently stable. There is always that nagging fear of, what if the original server is not actually fixed? What if the data sync missed something? In many enterprise environments, they will wait for a low traffic window, like 3 in the morning on a Tuesday, to perform a failback.
So, for Daniel, if he wanted to implement a miniature version of this for his home setup, what would be the most practical approach? He mentioned it might not be worth it for everything, but let us say he really wants his home assistant to never go down again.
For a home user, the most cost-effective way is probably using virtualization or containers. Instead of thinking about physical servers, he could have 2 low-power machines running something like Proxmox or a Kubernetes cluster. These systems have high availability built in. If one node fails, the system automatically restarts the virtual machines or containers on the other node.
But he would still need some kind of shared storage, right? Because if the data is only on the hard drive of the machine that died, the other machine cannot exactly reach in and grab it.
You are right. That is the hurdle for home users. Professional data centers use storage area networks, or SANs, which are basically giant redundant pools of hard drives that all the servers can talk to. At home, you would need a network-attached storage device, or use something like Ceph or replicated block storage where the 2 machines are constantly mirroring their drives to each other over the local network. It gets complicated and expensive very quickly, which is why Daniel is right that for most home stuff, it is overkill.
It really makes you appreciate the sheer amount of engineering that goes into making the internet feel like this permanent, unbreakable utility. We just expect our apps to work, but behind every swipe and every click, there is this massive, intricate dance of heartbeats, load balancers, and replicated databases.
It really is a marvel, and it is constantly evolving. We are moving towards serverless architectures where the cloud provider handles all of this redundancy for you. You just upload your code, and they worry about which server it runs on and how to keep it available. It pushes the complexity further down the stack away from the developer. We are even seeing the rise of DPUs, or data processing units, which are specialized chips that handle the networking and heartbeat logic so the main CPU can focus entirely on the application.
But someone still has to manage that underlying stack. The motherboards are still there somewhere, and they are still failing.
Oh, they are failing by the thousands every single day. In a massive data center like the ones operated by Amazon or Google, hardware failure is a statistical certainty. They do not even send a technician to fix a single server anymore. They wait until a whole rack of servers has enough failures to justify a visit, or they just decommission the whole rack and roll in a new one. The software is so good at routing around those failures that the individual hardware almost does not matter anymore.
It is like the difference between a single organism and a beehive. If one bee dies, the hive does not even notice. The hive is the unit of survival, not the bee.
That is a beautiful way to put it, Corn. We have moved from the era of pets, where we carefully nurtured and named every server, to the era of cattle, where we treat them as interchangeable units. And now maybe we are in the era of the hive, where the individual unit is almost invisible.
Well, I think we have given Daniel a lot to think about. Even if he does not turn his house into a multi-region data center, understanding the cascade of failover and failback really changes how you look at technology. It is not just about making things work. It is about making them stay working.
That is it. It is the difference between a hobbyist project and a professional service. One is about the joy of creation, and the other is about the discipline of reliability.
Well said, Herman Poppleberry. And on that note, I think we should start wrapping things up. This has been a fascinating dive into the world of high availability.
It really has. I always enjoy peeling back the layers on these topics.
Before we go, I want to say a huge thank you to everyone who has been listening. We have been doing this for over 600 episodes now, and the community that has grown around My Weird Prompts is just incredible. Your questions and your curiosity are what keep us going.
You are right. And if you are enjoying the show, we would really appreciate it if you could leave us a review on your favorite podcast app or on Spotify. It genuinely helps other curious minds find us, and we love reading your feedback.
You can find all our past episodes, including our archive of over 600 shows, at myweirdprompts.com. We have a search feature there, so if you want to see if we have covered a specific topic before, that is the place to go. You can also find our RSS feed there if you want to subscribe directly.
And of course, we are on Spotify as well. Thanks again to Daniel for sending in this prompt. I hope your new motherboard arrives soon and your smart lights are back in action.
Good luck with the repair, Daniel. And thanks to everyone for tuning in. This has been My Weird Prompts. We will see you next time.
Goodbye, everyone.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox Turbo.
Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts, as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify or visit myweirdprompts.com.